Hey everybody, we are back and we are about to start Chapter 9. Chapter 9 is all about alcohols, ethers, and epoxides. Couple of things. Number one, this is we're getting close to Thanksgiving, which is, basically kind of the end of the semester. This very well could be the last chapter. I'm not positive, but there's a good chance this is the last chapter of the semester. This is also going to be the second of two chapters on your third exam, which I'll send an email about your third exam. So you will have your third exam after this chapter. Also, I want to give a heads up. This is probably going to be the most complex chapter that we've gone over. There's a lot of stuff in here. Three different groups of compounds, and also another. We're really getting into the meat of reaction chemistry. So we're going to see a lot of new reactions this time. Some more SN1, SN2, E1, and E2, but in a very different context than we did with alkyl halides. So just be aware of that, and be sure to be on the ball in this chapter. First of all, what we're going to do is I'm going to introduce these three types of compounds, and then go over the nomenclature. Right? Anytime we introduce a new group of compounds, we got to learn how to name them. So let's go ahead and get into that. First of all, let me tell you what these guys are. Alcohols. I've alluded to alcohols before. We've talked about them in IR spectroscopy, of course, so you probably know what these are. These are going to be compounds that have OH groups. OH groups specifically attached to carbon chains. All right, so that's why we have the R. There's actually three different types of alcohols that we can go over at this time. We can have one like this. This is 1-propanol. This is a primary alcohol. Why is it a primary alcohol? It's the same reason why a primary alkyl halide is primary. The group of interest here, OH, is attached to a primary carbon, right? So it's primary. We can have secondary alcohols, and we can have tertiary alcohols. And just like we saw with alkyl halides, the identity of alcohol, the type it is, that will make a difference in the type of reaction mechanisms that it'll participate in. Doesn't follow the exact same patterns as alkyl halides, unfortunately, but it does make a difference. Okay? All right, the next two might be a little bit more new to you. Next one is called ethers. Ethers basically consist of an oxygen that has two alkyl groups, two different carbon chains bonded on either side, sort of like that. And there's a couple of different types of ethers. All right, we can have a situation where the two alkyl groups are exactly the same, right? And like in this one, this is diethyl ether. You see, we have two ethyl groups, one on each side of the oxygen. This is called a symmetrical ether. They can be the same or they can be different. So, something like this. Let's say instead of another ethyl group, we had a butyl group or something like that. That is called, you would think this would be called asymmetrical, but it's actually not. It's called unsymmetrical. That just doesn't sound right to me, but hey, I don't makes the rules, I follows them. So, there we go. Symmetrical and unsymmetrical ethers. Alright. Then we have epoxides. From year to year as I teach this course, I find that people dislike epoxides more than any other group of compound. I feel sorry for them. You know why? I think it's just because they look a little strange. People are kind of intimidated by them. Epoxides have a 3-membered ring in them that is composed of this structure. Little triangle, 2 carbons and 1 oxygen. All right, so any epoxide is going to have this group in it. And, as this is a ring, this does have 2 bonds on each of these 2 carbons. And these bonds can be above the plane or below the plane, just like that. They can have alkyl groups, they can have H's, they can have halides, they can have anything. They can have OHs, but they are there. The simplest epoxide would just have H's. And this one actually is got a special name. It's called oxirane. That'll be important a little later on when we get to nomenclature. But basically, an epoxide is going to have this group or some derivative of it. All right? All right, so that's what they are and what they look like. Let's talk about how to name them. And we're going to start off with alcohols. All right, and there's a couple of different ways to name alcohols. The most important one and the most widely used one is going to be the IUPAC method. So let's start off talking about the IUPAC method. All right, you're going to see some familiarity here, right? We're going to be looking for the parent chain first, and so we're going to be looking for the longest carbon chain. However, we're going to be a little bit more specific this time. You're going to look for the largest carbon chain that specifically contains your OH group. You're going to find that OH groups, alcohol groups, are considered more important in the hierarchy of nomenclature than alkyl groups or halides, right? They have priority. All right, so specifically, we need to look for the longest carbon chain with the OH, even if that's not the longest carbon chain overall. All right. Once you identify that parent chain, you need to number the carbons to give the carbon with your OH group the lowest possible number. And this is also a difference that we see from previous examples, right? Other times we went specifically to give any substituent the lowest possible number, just wherever it was. But here we specifically want to give the carbon with the OH the lowest possible substituent number, even if it doesn't work out for the other ones. So it gets priority. All right. Other than that, naming the other substituents, numbering the other substituents, you basically apply all other rules of nomenclature that you've learned thus far. All right. Now, one other difference here. When you name the parent chain, you're not going to name this as an alkane. You're going to name it as an alcohol. That's a little bit different. So what you do is you basically write the alkane name. So if the longest carbon chain with OH is, 6, you would write hexane. Except you would change the E of hexane to OL. So instead of being hexane, it would be hexanol. All right? Let's see this in action. Let's work a few examples. All right, let's take a look at this one. Okay. All right, so we're going to look for the longest carbon chain that has your OH group. I think, this one's pretty simplistic. It's going to be that. All right. Okay, we're going to number this specifically to give the carbon with the OH group the lowest possible number, right? Even though going left to right gives us our first substituent at number 2, remember the OH takes priority, so we would number it this way. Whoops. Let's see, 4, 5, 6. There we go. Okay. So we have a 6-carbon alcohol. 6 carbons is hexane, but since it's an alcohol, we call it hexanol. Now, you do have to identify where the OH group is, where the alcohol group is. Right? To do that, just put the appropriate number right in front of your alcohol name. So, this is hexanol. The 3-hexanol tells us that the OH is at number 3. And then you can just finish it out like anything else. We also have a methyl group at number 5, so this one becomes 5-methyl 3-hexanol. Very good. Let's try another one. Alright, if we're looking for the longest carbon chain with our OH, I think you'll find that it actually goes this way. Alright, and that's going to be 9 carbons long, so that is going to be nonane, but changed to an alcohol, so that is nonanol. That's not an easy name to say. It's kind of a tongue twister. Nonanol. Nonanol. Alright, if we number it, we're going to number to give the carbon with the OH lowest possible number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so again we have our alcohol group at number 3. So it's going to be 3-nonanol. And it looks like we have an ethyl group at number 5 and a methyl group at number 6. So let's just put them in alphabetical order. It's going to be 5-ethyl, 6-methyl, 3-nonanol. Alright. Not too hard. Again, just apply the rules as they're given and they should turn out okay. Let's try a ring. Let's try a cyclic alcohol. Let's try one like this. Okay? Now, the rules are basically the same here. Instead of looking for longest carbon chain with an alcohol group, you're looking for the ring that includes the alcohol. Okay? So this is cyclohexane, but since it has an alcohol group, it wouldn't be cyclohexane, it'd be cyclohexanol. And it is understood that the carbon in a ring that has your OH is going to be carbon number 1. Alright? No matter what else is going on, that one's going to be number 1. So you actually don't even have to write 1 cyclohexanol because it's always going to be 1 cyclohexanol, right? Because it's always understood to be number 1. So you can just actually leave it as cyclohexanol. And then you follow the other rules. So, we're going to number it clockwise to give the other substituents the lowest possible numbers. So we have a tert-butyl group at number 2 and a methyl group at number 3. So that's going to be 2 tert-butyl, 3 methyl cyclohexanol. Alright, so that's about all there is to the IUPAC method of naming alcohols. There is another one that's used fairly often for simple alcohols. It's a common name system. Does not work well for more advanced alcohols or complex ones, but for simple ones, it's used quite a bit. And it's the system itself is pretty simple. There's 2 basic steps. Number 1, name the alkyl group that's present. Basically, your alcohol is going to consist of 2 portions here. It's going to consist of the OH, and then it's going to consist of the alkyl group that's attached to it. So you name the alkyl group, and then add the word alcohol. That's it. So if you had something like this, right? IUPAC name for this one is going to be ethanol. The common name for it would be ethyl, because there's a 2-carbon alkyl group, ethyl, alcohol. Right? This one. IUPAC name for this one will be 2-propanol. However, there's a name you've probably heard this one. There's a name you've probably heard of before instead, called isopropyl alcohol. Yeah, this is like the alcohol, the rubbing alcohol that you get in a drugstore. Because we have an isopropyl group here, and then the alcohol group is attached to it. So isopropyl alcohol. So yeah, you'll see these used quite a bit, but only for simple alcohols. Alright, so that's alcohol nomenclature. Let's move on to ether nomenclature. Okay, so ethers are a little bit different in the fact that usually the IUPAC system for a given group of molecules is the most widely used one. Ethers are a little bit different because actually with ethers, most often you'll probably see the common name system for use. So we're going to go over that one first. Now again, just like with alcohols, really this only works well for simple ethers. It just so happens, though, that most of the ethers that are, used frequently in chemical applications happen to be pretty simple ones. So you'll see them tagged with their common names quite a bit, probably more often than IUPAC. All right, here's the steps in the common name system for ethers. Okay, all right, so in an ether, reminder, you have 2 alkyl groups, right? I'll just put a little R prime there, a little apostrophe, to kind of remind you of the fact that they are 2 distinct alkyl groups. First thing you got to do is you got to name both your alkyl groups. And you want to arrange their names alphabetically. Now you may ask, what if they're the same? Well, sometimes they are. If they're the same, just write the name of the alkyl group, but use the prefix di. Alright. Step 2, simply put, add the word ether. And that's it. Right? So if you have something like this is a really commonly used ether in organic chemistry for extractions and some other purposes. Right? In this one, we have 2 alkyl groups. They're exactly the same though, right? They're 2 ethyl groups. So since there's 2 of them, we'll just put diethyl, and then the word ether. Voila. This is diethyl ether. Fun fact about diethyl ether, it's actually pretty dangerous if you store it for too long. It can decompose and form peroxides, which can actually cause the thing to explode. So, next time you're handling diethyl ether, just keep that in mind. Mwahahaha. Don't worry, I'm not going to give you any bad diethyl ether, but it can be dangerous. Here's another ether that's actually been used a lot in teaching organic labs because it's actually a lot safer than diethyl ether, but can do a lot of the same things. You'll notice this is an unsymmetrical ether, so we're actually going to have 2 distinct alkyl groups. On the left side, we have a tert-butyl group. On the right side, we have a methyl group. So we just write them alphabetically. Tert-butyl, and then methyl, and then ether. And that's all there is to it. It's pretty simple. Okay, so that's the common name method. Let's talk about the IUPAC method. right? Now you can do the IUPAC method for any ether. We could have named those. We could have named those simple ethers that we just did, according to the IUPAC name as well. But this works also for complex ethers. In this one, what we do is we name them as something called alkoxy alkanes. Basically what this means is our parent chain name is going to be an alkane, right? So our parent name could be something like propane or butane or pentane or whatever, just like we've done in the past. And we treat, so here, let me write this down, this will make more sense. So what we do is we take one of these R groups. Sometimes it's R, sometimes it's R prime, so it's not always the left or the right one. We take one of these, let's just say this one. This one is the alkane parent, or one of them acts as the alkane parent. The other one, along with the oxygen, are treated as a substituent. And that is called an alkoxy group. That's the general name. The specific name depends on what that R group is, right? So let's say that R group was a methyl, right? So let's say we had something like this. In that case, since it's a methyl group, it would be called a methoxy. If we had 2 carbons, it would be called ethoxy, and so forth and so on. Okay? So that's what I mean by an alkoxy group. Alright, so how do you decide which one is the parent and which one goes with the alkoxy? Whichever one is the longest chain gets to be the alkane parent. The shorter one is part of your alkoxy group. Simple as that. Alright? So, for example, if you had something like this. Alright, we have 2 different groups. Right? We have this R group is obviously the longest one, so that's going to be our parent. And that's going to be 8 carbons, so our parent chain is octane. Alright, so we need to number this. 1, 2, 3, 4, 5, 6, 7, 8. We numbered it to give us our substituent, the lowest possible number. So we have a 2 carbon unit plus O, that's going to be ethoxy at number 4. So this one is going to be 4 ethoxy octane. 4 ethoxy octane. We could have one like this. On a ring. Same thing, right? Our ring, our 6-membered ring here is going to be the biggest part of this, obviously, so it's going to be our parent. So our parent here is cyclohexane. And we have a methoxy group on there, so this is methoxycyclohexane. Again, you can just assume that the OCH3, the alkoxy, is always at number 1. Alright? Very good. Let me show you one like this. Now this one has something else on it. It's got a chloro group on it. Remember in the alcohols I told you that the OH groups took priority over halides and alkyl groups? Same thing for alkoxy groups. They take precedent over halides and alkyl groups. Had a blank there. All right. So if you're looking at this group right here is the longest R group in your ether, so it gets to be the parent. We're going to number this actually from the the left-hand side, because that gives the OR group, the alkoxy group, the lowest number. All right, so this is hexane. At number 3, we have an isopropyl group attached to an O. That is isopropoxy, easy for me to say. And then we have a chlorine and a chloro at number 4. So if we put them in alphabetical order, 4-chloro, 3 isopropoxy, hexane. Very good. All right. Again, I really wish I had you guys in person, because, you know, visual and auditory feedback and all that good stuff. But if you have any questions, please let me know. All right, so that is it for ether nomenclature. Let's talk epoxides. Now, epoxides are a little bit different. First of all, there's actually 3 different ways to name them that are outlined in your book. I'm only going to go over 2 of them, because the third one is stupid, for lack of a better way of phrasing it. It's called the alkene oxide method. It works for only a very limited number of epoxides, and it's very obsolete. It's not used very much anymore. So I'm going to just focus on 2 ways. The first one I want to show you is probably the best one overall. This one will work for any epoxide, and that's the epoxy alkane method. All right, and basically, you can kind of figure out probably from this title that our parent chains here are going to be alkanes, so they're going to be named as propanes, butanes, pentanes, etc. And epoxy groups are going to be substituents. All right, so looking at the rules, what you want to do is find the longest carbon chain with your epoxy group. Now, what's kind of funny about this is that the carbons in your epoxy group also sort of double up as being carbons in the chain at the same time. All right, I'll show you, an example of this in just a minute. All right, number 2, number to give carbons with your epoxy the lowest possible numbers. And then use the prefix. I don't know why I put a parentheses there. That was weird. Ah, son of a nutcracker. Okay. Use the prefix epoxy for your substituent. Okay. Let me show you what I mean here. Let's say we have this. Alright, don't forget epoxides have the little triangle. Alright. Let's say this carbon has a couple of methyl groups attached to it. Okay, so what we want to do is find the longest continuous carbon chain with the epoxide group. That basically means that the longest chain that has this oxygen bonded to 2 of its carbons. Right? And so the longest carbon chain that has that oxygen is going to be that chain. Right? That's 3 carbons, so that's going to be propane. All right, we want to number this 3 carbon chain to get the carbons with the epoxy groups. In other words, the carbons bonded to that oxygen, lowest possible numbers. So that means you would go 1, 2, 3. And you see the oxygen is bonded to both carbon number 1 and carbon number 2. That has to be illustrated in your name. So what we would say is 1, 1, 2 epoxy, because the epoxy epoxy group basically belongs to both carbons 1 and 2. And then lastly, we have a methyl group here on number 2. I'm running out of room, so I'll just write it up here. 1,2 epoxy, 2 methyl propane. Okay? Let's try another one. Let's see. We had something like this. All right. Again, longest carbon chain with the epoxide group is going to be that. So that is 5 carbons. So that's going to be pentane. We're going to number from the left-hand side because that gives our epoxy group the lowest numbers. So we have an epoxy group at 2 and 3, and we have a chloro at number 3. Since chloro comes first alphabetically, we'll say 3-chloro, 2, 3, epoxy, pentane. Very good. Let's try a ring I guess these are rings. You can have actually epoxide rings attached to cycloalkane rings as well. They're kind of trippy looking. They're basically fused rings. They look sort of like that. Alright, but you treat it the same, right? So the longest continuous carbon chain, or in this case the ring, is going to be cyclopentane, right? That's the one that the epoxide is attached to. It should be understood that the carbons of your epoxide should be number 1 and number 2, right? So you want to put them in the order that then gives the other substituents the lowest possible number. So we're going to do it like that. So this is going to be epoxy, cyclopentane. You don't have to put 1, 2. You could. I won't count off for it, but you don't have to put it since it's understood there at 1 and 2. And then put 3-bromo in front. So 3-bromo epoxy cyclopentane. Alright, so that is the epoxy alkane method. Alright, the second method that I want to go over is naming them as oxiranes. And this only works for simple epoxides. And if you remember, this is all based off of this compound, right, which I told you is named oxirane. That's a common name for this particular structure. Simplest epoxide you can have, nothing but hydrogens attached to those carbons. Alright, so this one's a little weird. So in this case, what you do is you treat the word oxirane as the base parent names. So your parent name is always going to be oxirane here. And for numbering, what you do is the oxygen actually gets a number. It's number 1. And then the carbons, in some order, are going to be 2 and 3. Now, it's not always in this order where you have 2 on the left and 3 on the right. It depends. It depends on what else is attached. If you have substituents attached to one of these carbons, that increases their priority. All right. So, for example, if you had something like this, right? Let's say we had a chlorine attached. All right. Well, that means the oxygen is named 1. All right. Since the carbon on the left-hand side actually has a substituent, we want to give it priority. So we're going to name it number 2, and this one will be number 3. All right. So this would be 2-chloro oxirane. However, if we had something like this, right? In that case, that would be one. This one would be, oops. Yeah. This one would be number 2 because it's got substituents, and this one would be number 3. So this one would be 2, 2 dimethyl oxirane. Okay. So yeah, this works well for simple epoxides. If you get much more complex than this, then you're probably going to want to stick to the epoxy alkane method. Alright, so that is basically it for nomenclature of alcohols, ethers, and epoxides. If you have any questions, of course, as always, let me know, and I'll be happy to help you out. Next, now we're going to get into the real meat of the chapter. We're going to get into reactions, and you're going to see there's a nice, widely varied array of reactions that we could undergo. Alcohols are going to have the most types of reactions that you can have out of these 3 groups. Whereas you're a little bit more limited with ethers and epoxides. But there's going to be a lot of them to go over. I can't emphasize enough, at this point, stay organized. Make sure you're up to date on things because it's going to get real easy to get mixed up. Because, for example, the SN1 reactions of alcohols, they don't follow exactly the same rules as SN1 reactions of alkyl halides. So, be sure to be very proactive, do lots of practice, and be sure to have any questions on the ready for me at any given time. Okay. Other than that, I am done for right now, so hope you guys have a good one. See you next time.